So, hello, good evening. It looks like we have a participant here now. We can wait a couple of more minutes to see if anyone else join. Then we'll start. Okay, so I think we can start now. So, hello, good evening. I'm sorry, I think I was mute. So, I think we can start now. Good evening. My name is Umair Hussain. I am a PhD scholar in the Department of Mechanical Engineering at IIT Madras. Uh, and I'll be taking your doubt session for the Basics of Finite Element Analysis Part 2 course, which is a course under NPTEL initiative. Uh, as told in last week, in this doubt session, we'll discuss the content of the course taught in each week, and then we'll discuss some problems related to that part. And meanwhile, you're of course free to ask for any doubts that are coming from the course or within this discussion that we'll have. So, okay, then I think we can get started. So, in first week, we studied the basics of FEM discussed in the first part of this course. So, we studied a basic approach of FEM. So, what are the steps involved in FEM? We first go about discretizing, right? And so that means discretization means to split up the domain into different cells, elements, and nodes, like that. That's 2D discretization. Discretization, if it's 1D, it's rather simpler. So discretization basically means breaking the domain into small elements. Then we take the weak form. What we basically do is take the very residual form of the different given governing equation, and we reduce the differentiability requirement. This reduced differentiability requirement helps us in choosing simpler polynomial functions to uh, estimate the solution. So with that, then next task would be to choose the shape functions. And then with these chosen shape functions, we apply these in the weak form and get our system of equations. And finally, when we have the equations, we solve the equations to get the solution of the given problem for each node. So that's pretty much how the finite element method works. That was discussed in detail in part one of this course, and which we summarized in week one. Now we had to move on some more topics that we are going to cover in this course. So starting with the estimation of errors in finite element method. So since you know that FEM is a numerical method, so which means it's not an accurate method, unlike an analytical result. So it is bound to give some have some inaccuracy in the results uh, as compared to the actual or the analytical solution of a problem. So hence it is important to estimate the errors that are going to arise from our problem, and after estimation we proceed on uh, to remove those errors. So we first of all we should know what type of error we can get in FEM. So first of all, these the sources of this error is the approximation error. So as discussed in this step 3 here, we have to choose some shape function. So suppose, see, it's a linear 1D element. So it's a 1D domain. Solution should vary from 0 to 1. And suppose the exact solution looks something like this, u of x. And we discretize the domain, right? So so we discretize the domain. Suppose these are our elements. Uh, so between in this element we have to give have some approximation of the solution. That so we choose a polynomial as a shape function for this. So if we choose a linear shape function, we're going to get some result like this, which is a straight line. I will draw it. This is supposed to be straight line, right? So you see there's some inaccuracy here with the choice of our function. And suppose if I wanted to choose a quadratic or cubic polynomial, this would go much closer to this. I can't show it here. I'll just magnify this. Suppose this is the exact solution. This is the linear solution. Exact. And if we choose a quadratic function, it would be more closer to it. And as we keep on increasing or the degree of polynomial, we approach the exact solution. If this exact solution is some polynomial itself, then sometime after increasing the degree, we'll reach the exact solution. So that's how we find the error due to approximation of the polynomial function. So as we saw here, so degree here is 1, here it's 2. So as we increase the order of the polynomial or degree of the polynomial, the error is reducing. So approximation error is inversely proportional to the order of the polynomial. Okay, is that clear?
Yes, yes.
Okay, so yeah, so the next type of error is the computational error. Uh, so computational error is divided into two parts. First is the finite arithmetic error, and then we have the quadrature error. So computational error means the inaccuracy in our calculations. So if we are trying to calculate, uh, say some fraction, say want to in somewhere in our solution, we have to estimate this fraction. So you can write it as 1.33, or you can go on. The more number of decimal places you have for some number, the more accurate your solution is. So, uh, so there'll be, it's not just at one instant it would come, it won't cause much error, but these kind of errors would keep on accumulating if we'll have multiple instances of this kind of occurring, and it would be a considerable error then. So this is the finite arithmetic error. It's basically due to round off, we can say. Uh, okay, so in computers also, we know some of something known as machine precision. I don't know if you have heard that. So it's it tells the how many number of decimal places can the your machine store. So that also determines how accurate the calculation from your computer is going to be. That's something similar to this kind of error. Okay. So the next thing we have is the quadrature error. So quadrature error is basically due to numerical integration. So during the solution of our finite element problem, we need to you've seen that the weighted residual statement or the weak form basically is some integral of shape function. It's like times of number dvj by dx. So it's some kind of integral coming in your weak form. Can be like this, what I've drawn here. So, so you need to solve integration, and if you have to do it yourself, or if the and plus if the phi functions are simple polynomials, it's very easy to do. But if you have to do it using a computer, or the function is really difficult, the integrand coming here is a difficult one, then we can't do it analytically as we do. So we need to estimate these integration values using numerical integration. There are certain numerical methods to solve these integrals. So the most famous one that we use in FEM is the Gauss quadrature method. And apart from that, you have a lot of different methods: trapezoidal, Simpson rule, all those. You can use any. So, since it's a numerical method again to solve these integration, it's bound to have some error. There's some bound to be some inaccuracy. It would give you, to some extent, it would give you an exact solution for if these fees are simple polynomials. But if the integrand becomes something other than polynomial, there will be a lot of error there. So that is the error associated due to quadrature or the numerical integration. Then the third type of error is the computational domain error. So we if for an FEM problem we have a given domain. And as discussed, the first step in FEM is your discretization. We break our given domain into smaller elements like this. So this so since we know the shape functions and all the underlying calculations is defined for standard type of element, standard shapes, like simple uh, triangles, squares, or any other type of standard figures. Uh, but we don't have these calculations, these shape function or all those things defined for some random shape, some random curve. So, since we can only break a random shape domain into standard elements, there's bound to be some gap at especially at the boundary of the uh, our domain. So, like we are left with this area here. So, if in case of complicated geometry, uh, you'll bound to have some inaccuracy in covering the domain by your standard finite elements. So that is again a cause of an error, and we should keep in mind that this kind of error can only occur for 2D or 3D problems, where our domain can be a complicated shape. However, for 1D case, the domain is just a line, and a line you can break a line into smaller lines. That's it. What can you do about it? So there's no error coming in 1D case from the computational domain error, and these error can be reduced. This type of error can be reduced by reducing the size of the element, uh, or having more number of elements. So suppose we have a circular, or I'll draw bigger. So here we have some kind of arc here. So if I would want to draw full shape, something like this. If I want to cover this area with one triangle, suppose like this, then it would be difficult. But if I would want to cover it with two triangles, right now this is my error. But if I want to cover it with two elements, you see our error is reduced to this. So by increasing the number of elements, we can reduce this kind of error. And the other thing can be by using these curved edged elements. So this is something from the non-conventional finite element method, but there are methods, tools, and methods to do such thing. So after knowing the sources of these errors, the next thing we do is to evaluate these errors. In order to minimize, we need to calculate, have a quantitative analysis of these errors. So it's we there are certain type of ways in which we define the quantities of these errors. So first is the point-wise error. Though you must have seen in the lecture that it's not actually a kind of an error. It's not exact kind of valuation of error, but it is defined. So it's just the difference between the finite element solution and the exact solution at each point in the domain. So it's not a single value defined. It's actually multiple values. You define a point and you get an error for that point. So it varies point to point. The next is the max norm or the submetric error. So this is basically the maximum value of error from all the point error. So it's basically kind of something useful, which can be derived from the our pointwise error. So pointwise error in from pointwise error we can find all the errors at each point in the domain, and to make something some get some value that makes sense, we can just choose the highest of those values. That will give us an indication of how much uh, how high the value of error can be in the domain. So the max norm is basically the max value of error among all the point errors. Then there's another interesting way to define the error throughout the entire domain by a single value, which is known as the energy norm, energy norm error. So this is basically defined by this integral statement. It is basically the difference of the derivative squared, which is integrated over the whole domain of the solution, the FEM solution and the exact solution. So it's called energy norm because it consists of the squares of the derivative. And if we've seen, if you can make an analogy with the axial deformation problem. In that problem, you have u is the deformation. Then you take derivative of u, that is a strain, and strain is and the energy of your axial bar is basically proportional to the square of the strain or square of the derivative. So that's why this type of norm is called the energy norm, because it consists the square of the first derivative of the solution. So the next thing we have the L2 norm. The L2 norm is yet another way to define the error. So which is defined by this integral expression here. So it's basically the difference of the finite element solution and the exact solution, which is squared and integrated over the whole domain. So these are different ways of to comprehend or to get some quantitative expression for the error occurring in the whole domain. So I think this till this point is it clear? We discussed the
Yes,
different
yes.
types of error, and then the we understood how to calculate these errors.
Yes, yes, yes.
Okay, then we have the next thing is the convergence. So there are certain factors that influence the error in solution that we studied initially, and if we play with those factors or change those factors, the error reduces or increases. So if we change those factors in such a way that the error is reducing, and after certain some time, that the reduction error would reach would stop, and the error would reach its minimum value. And it after that, if we keep on changing that parameter in that same direction, there won't be any change in the error. So that is known as the convergence of error, something converging basically. So that means the error is reduced to a negligible value, and we can say at that point the FEM solution has converged to the exact solution or reached the exact solution. So this is known as the convergence of error in FEM. So there's to check when the convergence has occurred. There's a condition defined in this statement here. So whatever the error we are calculating, so right now it's defined as the energy now, U minus UHM. So the error should be less than this expression CH to the power P. Then we can say it is converged. So here C is some constant which is independent of the FEM solution or the exact solution. H is the element size and P is the rate of convergence. So we'll see there's an expression for this P. So P is basically dependent on two main things. First is the order of differential equation, and the next is the degree of the polynomial or the shape function we are using. So 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 right now in our problem, they, there are two factors that that we can control in this expression. That is the H and P. So H is basically the element size. If we reduce the element size, our error reduces, as we have seen in the case of our computational domain error, or even in case of other type of error, it will the element size reduce. It would the error would reduce. We'll see how. And then we have if we increase the P, that will also change the error, reduce the error. So there are basically two types of convergence defined on this. One is known as the H convergence, and another is the P convergence. However, if we talk in terms of labor, the P convergence is less laborious in terms of man labor. We don't have to do much work. We basically solve the FEM problem using a computer program, and it's not difficult to define a higher order polynomial shape functions to the program. However, it is the discretization of the domain is a separate task. So this usually this increases man labor. So it is it is not always convenient to do H convergence. So this should be kept in mind. So we also studied certain characteristic of the FEM result regarding its accuracy. So, firstly, that FEM under predicts the displacement U. Then it over predicts the energy and over predicts the stiffness. I'm not sure about stiffness part because I think it should be under predict because stiffness is equal to force time displacement. Okay, so it's inversely proportional, right? Yeah, so I think it should over predict. Okay, anyway, you can see that later. So, we'll see how these statements are true. Basically, you have to verify these claims. So first of all, any type of general differential equation can be signified by this equation here in block this block. So if we change the value of m to 1, we'll have simple xj bar problem or the heat equation. If we have this m equals to 2, we have this beam problem, like that. So we consider the case of m equals to 1. Uh, so for a case of m equals to 1, this equation 1 here is the weak form of the equation. So uh, and then if we consider this function IU, so IU is basically defined as these two quantities, where first quantity is nothing but the internal energy. If you understand the analogy of an axial bar, so half A times the square of the displacement, the first derivative displacement. This is nothing but the strain energy, and so this is known as, this is considered in general terms as internal energy, and the other part is the external work. So this is nothing but the total energy. IU is, so for some general problem, this can be taken as the total energy. So to minimize this total energy, we take the variational derivative of this I, and if we solve, we go to the weak form, right? So basically, we know that the strong form. I'll write it here. You already know that the strong form. This is equivalent to the weak form. Thing. In the very basics of FEM, we know that these two forms are equivalent. And right now, we also prove that this functional IU, sorry, the variation of this function put as 0 is also equivalent to these two. So this thing means the same thing. So so after once we have established this, uh, so we know that IU defines the total energy of the system, right? So if we take the IU for the FEM solution, the FEM solution, and take it different with the analytical solution, we get I mean the exact solution. We get this quantity here, where this first term is obviously positive, is of course positive, and this term is also either greater than 0 or equal to 0. Equality comes in case our solution converges and our FEM solution reaches the exact solution. So we get that the energy coming from FEM minus the energy coming from the exact solution is always positive, which means that our energy from the FEM solution is always either greater than or equal to the energy from the exact solution. So equality comes in for converged solution. So this is the proof that FEM always over predicts the energy of the system. However, if we think about it, there is one more way we can guess this thing intuitively. So suppose we get the derivative of this FEM solution, right? So whatever the derivative from this FEM solution is, if we take the difference with the exact solution, so this would be some either positive or negative number. But if we take it square, it would be definitely a positive number, and it's almost same as this. Okay, so yeah, so the error coming from energy would be either positive or negative. But if we take the its square, it's always positive, and which is uh, and in the case of energy, we take the square of the terms. So basically, we'll always have uh, a positive difference of energies. So yeah, this is clear till here. We can move forward.
Yes.
Anyways, if there are any questions coming up here, we can all we can take any questions. Otherwise, we'll move forward. Okay, so we can move forward then. So we had this criteria for convergence defined earlier, that there should be less than this ch to the power p term. So if we try to plot a log plot for this function here, so we'll see that the log of error is increasing as the log of h, or the element size, the log of element size is increasing. So here we can clearly see that as uh, we increase the value of h, the log of our error increases. Basically, our error increases, right? And the next thing is that is the slope of this log graph. So these higher slope line is, so suppose say p equals to 1 is here, so this line p equals to 2, this line p equals to 3. So as p is increasing, we have a higher slope line, right? So again, we are getting a higher rate of convergence. For a higher value of p, if we keep on increasing the size of element, we'll reach the minimum error. We converge solution faster. So we get a couple of also. I forgot to mention that the expression for p is here. So where k is this degree of interpolation function, or degree of this point, the polynomial we use, and m is the this is actually the half of the order of differential equation. So basically, the order of differential equation is known as 2m, twice of m. So we get a couple of observations from this this graph here. That first of all, if p is increasing, our convergence increases, right? And of course, p is proportional to k. The higher degree of interpolation function we use, the we get early convergence, faster convergence. So that was discussed earlier also. And as we basically let it reduce h, it's better to say reduce the element size, get a faster convergence. Even though if we saw that the p convergence is faster, why is it? Why p convergence is faster than h convergence? We can get an answer for this.
P actually denotes the degree of the polynomial, I believe. So if the degree of polynomial chosen is nearer to the exact solution, then that is the reason of less number of iterations, and convergence will be faster.
But your exact solution will not always be a polynomial. It can be any random function. Why
But
P is actually causing faster convergence compared to H?
maybe because it's computationally expensive if we increase the number of elements.
P is computationally expensive. Yeah, right. That is true. But here, if you look at this expression, we
Okay.
it's I'm not. My question was not actually how why physically it is happening, but we'll see this equation. From this equation, what can the values of H and P tell you? So if you can see that the error is actually linearly proportional to H, but it's the P proportionality is exponential. So any change in P causes exponential change in error. So that's why P convergence is exponential basically. So that's why P convergence is faster.
Okay.
Okay. So
Yes. 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 Okay.
okay, thanks, Anil. So then we have the third observation that P goes down as M goes up. So of course, if we have a more complicated higher order problem, we have a slower convergence, right? So that's why P with higher order differential equation, we can see from this expression as M increases, P goes down and convergence is slower. Also, yeah. So L2 now we saw that is depends on the difference of the solution values. You see it here. It's basically the difference of the values. However, the energy norm is difference of the derivative of the values. So so the L2 norm converges faster, right? And then so that's how we have this order of convergence. Uh, the the and the solution values converge faster, and consecutively they higher order derivative first, second, third. The convergence for them goes on slower. So let me clarify this point four. I think I make myself clear. Point three and four actually are combined. So for as m goes up, p goes down. So m increasing m basically reduces the convergence, and increasing m is basically the order of equation or the derivative. The higher the derivative we are dealing with, the slower the convergence is. So that's why if we see the in L2 norm, it's the value of the difference of the values of the solution, and in the energy norm, it's the difference of the derivative of the solution. So that's why L2 norm is going to converge faster, since it's related to the values. And likewise, if the higher derivative we'll go here, the slower the convergence we'll see. So if we are solving a problem, we just don't stop after seeing the error in the solutions. Suppose solution U, we don't just see the error in U and when it is converging. It would converge much faster. If suppose in any problem the result that we are concerned about is the second or first or second order derivative of the solution, then we would need to check for their convergence also. So since they converge later than you, so we need to ensure that the error in those the higher order derivatives is also converged. So the criteria of convergence, that's why is actually dependent on what our actual need is from the problem. So that's how we decide the convergence of the problem, not just by simply observing the error in the solution values. So I think we finished this week's lecture at this point. We covered till here, and I hope you must have covered all this week's content by now. So we'll see if we have any doubt here. We can wait for some time, and we can then move ahead with solving the problems. Can we can have a 5 minute break also, and meanwhile in that time I'll answer any doubt if there's any. Okay, then I think we can move forward. There are no doubts coming.
Sir, about this L2 convergence.
Yeah.
L2 convergence and this strain energy convergence. Basically, what is the physical meaning of these two? Why is one converging first and another converging later?
So basically, these are the way of representing the error.
Okay,
It doesn't matter. It doesn't actually physically mean anything. But
okay,
L2 norm is a way to represent. So in FEM solution, I'll show you that.
okay,
Suppose this is your FEM solution, and this is your exact solution. So throughout the domain, you'll have some error. Suppose, uh, let me do it like this. FM solution is coming out to be like this and this, right? So, so error is varying at every point in the domain. At some point, you don't have any error like these points here, but at some point, you have a huge error like this. So, in order to quantify those all multiple point errors, we define a common quantity which comprise which gives common one number that represents all those different errors. So L2 norm is just one way to represent that, and energy norm is another way to represent that. And the way we have defined is actually affects how fast those errors would converge. Basically, it's basically the way of defined. There's nothing more physical to it, as per what I know. Not sure they can be more.
okay. Thank you.
Okay, no problem. So we can move ahead with the problems. So yeah, so I think we've discussed this. So energy predicted from FA solution is dash than that from the exact solution.
More.
Right. Okay, good. So this is something from numerical integration. I thought I think we're going to study it later, but I thought I'll introduce this to you before because it's quite relevant to the error thing. So how many number of points are required to exactly calculate the numerical integral of the following polynomial? So do we have an answer for this? So, as I might have mentioned that for polynomials, we if we keep on increasing our accuracy, uh, I mean, if we keep on increasing our number of points, we at some time we can reach the exact solution. In case of numerical integration, not for not talking about FEM. Uh, but if we are not if we don't have polynomial integrand, then it's not possible. But for polynomial we can. So there's an expression to relate the order of the number of Gauss point in the order of polynomial, which is defined by this. So this is the number of points, and this is degree of polynomial. So here, what is the degree of polynomial for this integrand given here?
3.
Yeah. So the number of points is 2. So we can just use two Gauss points or two integration points to exactly calculate the integration integral value for this integrand using our numerical integration. Okay, so this is not from what we studied so far, but we'll study it later in the coming weeks. Sure. So to calculate energy norm, we had some expression. We defined the term m here, which I think something like so yes. So so we had the term m defined here. So what would be the m? So first of all, can you just tell what does m depend upon?
Is it the degree
Degree of what?
polynomial? The
No, no, no. It's actually depend on the order of differential equation.
okay. Okay.
So this is we'll write this differential equation more conveniently. Basically means so. So what would be the order of this differential equation? Suppose we consider k as constant, we'll have we have this here. So what would be the order of this differential equation?
Order will be 2.
Yeah, right.
Degree will be 1.
Right. So which is equal to m. So that's the case. That's how we find the order in the 2D or 3D problems like that. So I'm assuming it right now is graded to be 2D. That's how I validated this differential equation. So for this type of problem, we'll have value of m equals to 2, and that's how we'll calculate this energy now. Okay, I'm sorry, it's not equal to 2. Okay, order is 2. So m is actually equals to order by 2. So m equals to 1. Yes, yes, right. So m equals to 1 here. So this is some basic exercise to so L2 norm is nothing, not something new introduced here. It's a very general, very popular topic in linear algebra. So, uh, so how do we find an L2 norm of a vector? For a vector we find so we, so in case of general vector, how do we define L2 norm?
Do we take the sum of the squares of
Sum of squares of
the vectors in the symmetric space?
mm, yeah, you're quite there. Oh, there's
And then
something.
take the under root.
Yeah, yeah, right, right. So this is nothing but the length of it, right? So it would be like square, 2 square, 5 square, square root of it, 4 plus 1, 5. So that's just basic revision of L2 now. So now we'll try to calculate some errors that we learned in the this week's content. So suppose we are given here a function ux. The exact solution here is ux. Hello, yes.
বলছি এটা হয়ে গেলে একসাথে বসে দেখবো। আমরা দেখবো তো, এটুকু ধৈর্য ধর। আমার তো তোর সাথে দেখতে ভালো লাগে, ধৈর্য ধর, ওরা আনন্দ করে দেখবো, একটুখানি ওয়েট কর।
Hello, sir. Can you please unmute yourself?
তোকে চকলেট দিলাম।
এই এক মিনিট,
কি?
এই হেডফোনটা আমার
এত যত্নে থাকবে তোর হেডফোন?
এই বাবা কফি খাবি না যেসব কথা হবে।
Hello, can you
কফি
please
খাবে
unmute
তো?
yourself, sir?
এইটা এটা খাওয়া যাবে না,
কোন
এইগুলো পচে নষ্ট করবে তোর মা।
এখন আমি ভুট্টা ভাজবো, সরো। তরকারিতে করা যায়, আমি এখন এই দুটো ভুট্টা ভাজবো।
ওটা ভাজ।
সাইড 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 কফি খাবে তো? বলে যা। আর বলো।
বলছি
So,
ওই কাজ শেষ করো, ফোনে কথা বলার সময় না বেশি বক বক করতে নেই, শর্টে ছাড়তে হয়।
আমার আছে
okay, thank you. So, we have an exact solution here as ux equals to sine x, which we are trying to approximate using some function. Say here is uh, this 2. I'm sorry, it's not a linear function, it's parabola. Suppose we have something like that. I'm not sure what it looks like. And we are defining it in the domain 0 to pi. So can we find point errors here? But x equals 0, pi by 4 and pi by 2. So we'll start with x equals 0. So error is, here is, so what's u h at x equals 0? 0, right? And ux is also sin x is 0. We don't have any error at x equals 0, right? So then we have x equals to pi by 4. So at pi by 4, what does the UH becomes? Sine at pi by 4 is 1 by root 2, right? Not so sure.
Yes, yes, 1 by root 2.
Thanks. So we have pi minus pi by 4 is 3 pi by 4, and then we have 3 pi square by 4 divided by 10 and 1 by root 2. So this becomes 3 pi square by 40 and a 1 by root 2. So I would need a calculator for this. If anyone gets an answer meanwhile, you are free to answer. So I got an answer here. 0.033. I hope this was right. Okay, then we have another point here. So I'll calculate above. One error rate x equals to pi by 2, right? So u h at pi by 2 becomes pi minus pi by 2 on 5 minus u at pi by 2 becomes, what is sin pi by 2? So we have pi minus pi by 2 again, pi by 2, pi square by 10 minus 1. So what I know, pi square is almost equal to 10. So pi square by 10 minus 1 is minus 0.013. So even further reducing error here. Should actually come out around here. Then it would go right. It's negative. So anyways, we got our point here at these 3 points. X equals 0, x equals pi by 4, equals to pi by 2. So I hope it's clear till here.
Yes.
Okay, thanks. Okay, then can we find the L2 norm for the previous problem? First of all, what's the what is the formula for L not L2 norm? Can someone guide me? So if we can get any answer from our new participant. Sorry. So while try to write, please guide me. So it is defined, I think, from what is domain 0 to pi, right? Integral is from the range of the domain. Then we have our h minus u squared dx. We take square root of this. I hope this is the formula. I'm not, I don't remember it very well. So let's check it.
Yes, I think it's correct.
Okay, thanks. So yeah, then I think it's going to be tough. We have a sine function here. We'll try anyway. See how long we can go here. So we have UH's, it is 2x 2x times pi minus 6 right minus sin x squared, like half of this. So we're going to have square of sine function and product of polynomial and a sine function, for which we would need multiple integration by parts, and it's going to be a tough thing to do with my hands. Then I'll go to my calculator. So meanwhile, if anyone else come with a solution, please let me know. So we have integral from 0 to pi 2x into pi minus x divided by 5 minus sin x whole square. Yep, I got an error of 1.52. Okay, sorry, I forgot to take its square root. 1.5. So we take square root of the answer. 1.23. So that's what I am getting. If anyone else is getting a different answer, please let me know.
It's correct, I think.
Okay, thanks. Okay, so if there are no doubts, we can move forward. So, which type of convergence is more suitable for a complicated geometry domain? So, first of all, what are the type of convergence we have? So, we have two types of convergence. Okay, Do we have any answer for this? So I'll tell the first H convergence. We have P convergence. This will lead to element size, and this will lead to so these are two types of convergence. So what parameter among these we should uh, change or control to uh, to get faster convergence in case of a complicated geometry domain? So basically we can control two things. First is we change the element size, and all I mean to reduce the element size to get a faster convergence, or we increase the degree of polynomial to get a faster convergence. So for a complicated geometry domain, what do you think is more suitable?
Maybe if we use a very small element sizes, it can approximate the geometry better, and convergence will be faster.
Right, right, exactly. So the for simpler geometry like this, you can just have two triangular elements. That's fine. For this, you can't have two triangular elements. To get a lesser error, to do something like this, some kind of meshing like this. So it's yeah. So uh, its convergence seems to be better for case of the complicated geometry domain, right? So yeah, among these plots, which one do you think is makes more sense uh, for the energy strain energy calculation from the FEM study?
Since the strain energy is always positive, I think it's A.
Hmm, strain energy is always positive. Who said that? Why do you think strain energy is always positive? Did we discuss that?
Since it's square of the term, I think square of the displacement, basically
Yeah,
square of the strain.
you're actually there. Yeah,
Uh,
the thing that's positive is this: the total energy from FEM minus. So which means that the energy calculated from FEM will always be greater, or we can just write this greater than the energy from the exact solution, right? So which means so what does this plot is telling you? Plot is telling you as you increase the size of the element, what is the change of your energy from FEM, right?
I think it will increase as the element size will decrease. Increase on increasing the element size, it will increase.
So as H increases, the error would also increase, right?
Yes.
Going away from convergence, isn't it? Or we can
Yes.
say as it reduces, error reduces. And if error is reducing, then so this full statement is actually IUH is greater than or equal to IU. So as we have a higher value of H, the error is more, and I is much greater than I. IUH is actually greater than much greater than IU. But as we reduce the value of H, the error reduces, and I would tend to approach. Sorry, IUH would tend to approach IU, right? So actually the energy would reduce. H would reduce, right? Which is happening in this case B here. So as we are getting reducing the H is reducing in this direction, our energy is also reducing, and it is converging at this point. So it is energy reducing to the uh, energy from the exact solution, right? So IU would be a straight line. If we try to plot, suppose this is actually a plot of IUH. We'll talk about that. So what would be the plot of IU with respect to H? It would be a straight line, because exact solution doesn't care about element size, right? It is always the energy calculated from the exact solution would always be same, no matter what the element size is. It's a straight line. So as H would reduce, this IUH would also reduce, and it would converge. It would converge at this point here. So this plot makes sense. Others do not. First one, energy is increasing. If as H is reducing, energy is increasing. This is wrong. And in second plot, the energy is increasing and then decreasing. That will also not happen. If it converges once, it doesn't diverge. Okay. I hope this concept was
Yes. Yes.
clear.
Okay. Yes.
Okay. I'll wait if there's any question. Okay, so if there are no questions, I can then move forward. Yeah, so we did come across something about taking variations in this week's content. So I thought to introduce this variational derivative again. So this operator here is known as variational operator, and if you try to apply it on some any algebraic equation, it would work quite similar to your del or derivative operator. Uh, so using the same rules like your addition rule, your multiplication rule, it works the same way. So we take variational derivative. So how do we take variational derivative of some differential equation with this? So I'll remind some principles also. So variational derivative of x equals to. So these are certain rules we follow. And while proving the equivalence of and your weak form, I use the same way to calculate this variational derivative del I. Excuse me. I remember it was done a little differently in the class, but I used the variation operator in this way. Yeah, I need to explain this in much details, but that's how we go on. So, can anyone answer how do we proceed here? It's not actually functional. It's a differential equation. It's the question is actually framed wrongly. My apologies. I think this is a better framing of this question. So how do we go about this? Can I get any help? So using this rule here, you can transfer this variational operator inside the derivative, right? Can somebody write this as like? So this is actually simple demonstration or how to use this variational operator, uh, and it gives us an idea to find the variation derivative of any given function, which was as you saw it was helpful in finding the variation derivative, the first variation of our total energy functional. So this is clear. So if there are no questions, we can move ahead. So we need to find P, right, of a first. So what's the expression for P? Is it K minus 1? Sorry, K plus 1 minus M. Can I get a confirmation? I'll just check the notes. Yeah. So for a first order equation, so first order equation, I'm sorry, it's not first, it should be second. Right. You usually deal with second order equation or fourth order equation FEM. So for second order equation, it means value of M equals to 1, right? And we are using quadratic shape function. Essentially means value of K equals to 2, right? So what should be the value of P here? Plus 1 minus 1 at 2, P equals 2. So and we need to find the convergence rate if element size is 0.2. So this is H. We given C equals to 1. So what is the formula for convergence rate? So convergence rate should be less than C times S to the power P, right? So this is so C equals 1, H equals to 0.2, P equals to 2. So what are the convergence rate? Right? So our error should be less than this value for it to be converged. Okay. So yeah, then we have the next question. For a simple elliptic partial differential equation, the error of at the nodes is it larger than the rest of domain or smaller than the rest of domain, negligible or zero? Can we get an answer for this? So we are waiting for an answer for this question. Okay, so for a simple elliptic partial differential equation, the error at nodes is actually it's zero. Usually for simple kind of differential equations, simpler problems, we usually get zero error at the nodes. And if we will see so that for such cases, we also observe that the error in the derivative first derivative of the solution is actually zero at the quadrature points, the Gauss quadrature points. You might see learn more about it in the coming lectures. But I'm giving you a hint about this. So again, we studied this initially. What type of error is not present in a 1D FEM solution? So we have how many types of error? Three main types: approximation error, computation error, computational domain error. So of these three, this third type, computational domain error, is actually what is only seen 2D or 3D domain. So I think this is pretty clear. I don't think anyone should have any doubt for this. If there's, please let me know. Feel free. Otherwise, we can move on to the next problem. Okay, so we did find some types of error in problem 5, right? So now we found the, yeah, found the point error, then we found the L2 error. Now we need to find the energy error. So the energy error is actually given by the expression right. I hope this is the right expression. Let's check. Okay, yeah, so we have derivatives of the exact FEM solution. So M, I think we have not mentioned anything about the differential equation. So for simplicity, we'll consider M equals to 1, right? So what do we get here? Right, so our UH was, I think it was 2x into pi minus x by 5, right? Just the pi minus x by 5. So what is the first derivative of UHX with respect to x? It will be, I think we'll get 2 pi by 5 minus 2x squared by 5 is actually x by 5, isn't it? 2 pi minus x, sorry, 2 pi by 5x, right? 2 pi by 5 and 2 square by 5 is x by 5, right? Then exact solution is sin x, and simple derivative of sin x is cos x, right? So we have then 2 pi minus x by 5 minus cos x whole square power half, right? So again we have a big sturdy expression coming in the integrand, and it could take hours to solve this using integration by parts. So I'll just use my calculator here. So I'll get 2 pi minus x pi minus 6 divided by 5 minus cos x whole square, and integration limit is 0 to pi. So we have 0 to pi, 2 pi minus x by 5 minus cos x whole square. We get square root of 0.3. That's 0.336, right? So yeah, that's how we calculate the error in energy now. So I hope uh, this was clear. If there's any doubt, please you're free to answer. You're free to ask right now. If there's any doubt regarding this question or the any other questions, we can address them now.
Hello.
Yes, sir.
Here, even if we differentiate with respect to x of un, then that is, I think, 2 by 5 into pi minus 2x.
If 2 by 5 x into pi minus
2x is 2 actually missing. 2 pi
2, It's actually x square, right?
4x by 5.
It's actually minus 2x square by 5, isn't it?
Huh?
Okay, okay, sorry. I think it will be 4 will come here, right?
Yeah, 4x by 5.
Yeah, 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 right, 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 right. I missed that. Thanks for pointing it, sir. So it's 2 pi minus 4x. Yeah. Thank you. I'll just correct this. Find the answer again. Meanwhile, if anyone gets the answer, let me know. Yes, so we have 0 to pi, 2 pi minus 4x by 5 minus cos x whole square. Oh, that is actually equal to 4.79. Square root of 4.79, which gives us 2.18. 2.85. Okay, so yeah, this should be the correct answer. Yes, so if there's any doubt till here, you are free to ask. I'll try to answer it now. Meanwhile, I didn't get any chance to interact with the audience here. So if you want to introduce yourself and tell me your motivation for this course, I would be happy to know.
Uh, my name is Vikas Juaddar from West Bengal.
Hello, sir.
I am in a polytechnic college in Department of Mechanical Engineering as a lecturer.
Okay, nice to meet you, sir.
Thank you. Actually, I was able to join the class late, but whatever I have seen, the solution of the problems and others was really very good. I
Thank you so much.
enjoyed a lot of and learned a lot of thing also.
Thank you so much,
Actually,
sir. It's really appreciated.
ET course finite element was a subject. So
Yeah.
after a long time, I am again enjoying the subject.
Okay.
Like
It's it's nice
future,
to
I will
know.
learn again more and more. Thank you.
Yeah, yeah. I'll be waiting for you to join sessions. And
Yeah.
you are quite senior to me. It would be a great chance for me to learn from you as well.
No, you are actually already a genius, and um, so it is. We are so much lucky that we are getting the chance. Such talented and beautiful person are taking the classes.
Oh, thank you so much, sir. Thank you, really.
Okay, welcome.
So, I think we're out of time here. So, I think we can conclude our session here now. Uh, we'll be meeting soon in the next sessions. If there are more doubts, we can address them there. And so next week we'll meet up again at the same time, and hopefully we'll discuss the content week 3. So I hope to see you guys there again. and it was a nice, wonderful experience to spend this time with you and to demonstrate whatever I could from this course. Thank you so much, everyone. You're free to log out now. Then I'll end the session.
Okay, okay.